Hi everyone, my name is Alex Baluta and I'm from York University. Today I'll be presenting our machine learning based approach for interference modeling in cloud native applications. Software applications are frequently deployed on cloud platforms like Amazon Web Services. These cloud native applications often follow the microservice architecture. Microservices are frequently deployed in containers, which are co-located on shared virtual machines. Co-location can improve resource utilization, but it also can result in resource competition, which can cause performance degradation, also known as performance interference. Our proposed ML-based techniques model performance interference in cloud-native applications. By modeling the impact, mitigation strategies can be employed when necessary. Our contributions to that end are static and dynamic ML-based interference modeling techniques that generalize to unknown interfering applications at runtime, have minimal model training overhead, and outperform competing state-of-the-art modeling techniques. Furthermore, we conduct a comparative analysis between the static and dynamic ML interference modeling techniques. Techniques for interference modeling are either static or dynamic. The figure presents the high-level overview of our static interference modeling technique. The target monitored application consists of multiple tiers of microservices. Interfering applications can be co-located on the same virtual machines as the target application. As seen in the figure, our technique runs in two phases. The first phase is the training phase, where controlled experiments are run to train our ML model in an offline model training environment. The workload generator tool is used to send workload to the target application in order to generate a wide range of resource utilization levels. Additionally, the metric monitor serves to collect the metrics of concern. With the metrics for the target application obtained, we employ an AutoML framework to train ML models. In our experimentation, we use the H2O AutoML framework. The framework outputs the best performing ML model from the set of models it trains. Now we move on to the second phase where the trained model is deployed to model performance interference at runtime. In the second phase, we monitor metrics of concern at runtime as a microservice serves client traffic. This data is used to invoke the deployed ML model, which in turn predicts the application response time subject to any interference that may be present. As for our dynamic modeling technique, there is only a single phase, the runtime phase. Model training and invocation are both done at runtime. The setup is largely the same as in the static modeling scenario, but we now have an additional component called the model manager. The model manager is responsible for the end-to-end life cycles of models trained and deployed in our runtime phase. The model manager employs a model deployment strategy as defined by the DevOps team that defines when a model should be trained. The strategy triggers the model training process when required, and the newly trained model replaces the old. The model prediction process then invokes a new model to obtain at runtime performance predictions. Our dynamic ML technique utilizes a sliding window model deployment strategy in conjunction with the H2O AutoML framework. Sliding window techniques configure a fixed time interval. Model training is conducted within that time interval for whatever data is collected. With a balanced interval, we can construct well-performing models while also minimizing required model training time. By utilizing a sliding window for model training and deployment, changes in the cloud environment can be captured in a dynamic fashion. Here I present an overview of our results with additional discussion in the extended version of this presentation. To evaluate our techniques, we ran a set of experiments in the AWS cloud. We leveraged several microservices as our target and interfering applications and co-located them on virtual machines. We sent varying workloads to these co-located applications, monitored metrics of concern, and used those metrics to evaluate our interference modeling techniques versus competing techniques. To that end, we used the mean absolute percentage error as the evaluation metric. Competing techniques were the layered queuing model, linear regression, and the Gaussian process model. As you can see in the graph, both our static and dynamic ML techniques outperformed competing techniques in several cases by wide margin. In the dynamic interference modeling case, our technique outperforms competing techniques by at least 1.45% and at most 92% across the various scenarios. Now recall that we evaluated our static interference modeling technique against linear regression and layered queuing models, both of which have been used in prior works for microservice performance interference modeling. Our static ML modeling technique outperforms these by as little as 14% and as much as 1200%. In all scenarios, AutoML selected the gradient boosting machine as the best performing ML model considered. It's important to note that static interference modeling works well when the application owner knows what interfering applications may be co-located on the same virtual machine as the target application. The results above represent a scenario where the interfering application encountered at runtime is the same as that encountered at training time. Our dynamic interference modeling technique addresses these shortcomings of the static techniques. Nevertheless, this is a useful scenario when the application owner wants to scale manually or automatically known applications and would like to see the effects on another application. Now, for a more detailed evaluation of our dynamic ML technique for interference modeling, recall that for dynamic performance modeling techniques, model training occurs at runtime. Consequently, the active model is likely to be employed when there is runtime interference from the same interfering application encountered in model training. Should the interfering application change at runtime, the new interfering application is unknown to the active model. However, given the dynamic nature of the sliding window, subsequent models trained at runtime will detect the new interfering application's impact and their respective model training. As a competing technique that is also dynamic, we leverage the Gaussian process model with a sliding window deployment strategy. We further evaluate our dynamic ML technique against the layered queuing model, which itself is static. Our dynamic ML technique outperforms competing techniques in mean absolute percentage error by 1.45% to 92%. Gaussian process comes in second place and outperforms layer queuing models in 4 of the 6 scenarios. We further conducted a comparative analysis between the static and dynamic ML techniques for performance interference modeling. It's particularly noteworthy that the static ML technique outperforms its counterpart dynamic ML technique. However, the success and applicability of static techniques is limited to scenarios where the application owner knows what interfering application may be or are co-located with the target application. If we consider the generalized form of our static AutoML technique, where the interfering application is unknown at runtime, we found the mean absolute percentage error degrades by approximately 2 to 6 times. It's therefore unwise to use static models to quantify interference impact induced by unknown applications. However, the dynamic AutoML technique performs comparatively well with respect to its static AutoML counterparts. While it does not outperform the static AutoML models with visibility of the co-located applications, the dynamic AutoML models perform within 2% and 12% of their counterpart. The dynamic AutoML technique does not require visibility of co-located interfering applications, so it can account for changing environment conditions. Also, it does not require a long training time, unlike the static technique counterparts, which required 40 hours to collect the training data. Therefore, dynamic modeling is highly recommended and practical for modeling the interference caused by applications unknown at runtime. We note two threats to validity for the ML interference modeling techniques. As an internal threat, if the configured number of data points considered in the sliding window is set too small, the mean absolute percentage error of our trained models may deteriorate. If it's set too large, model training may become too slow to keep up with changing environment dynamics. As an external threat, our experiments were conducted in a single availability zone. In the AWS cloud, our experimentation considers multi-VM deployment strategies within the same availability zone. We do not consider deployment strategies across multiple availability zones. In conclusion, we proposed an ML technique that can be used in both static and dynamic modeling for performance interference quantification in cloud-native applications. Notably, the dynamic ML technique is effective in modeling performance interference and outperforms competing state-of-the-art techniques by 1.45% to 92.04%. For future work, we intend to integrate our performance interference quantification techniques with microservice placement strategies. Quantifying the potential impact of microservice co-location provides a meaningful signal to drive suitable microservice placement. Placement strategies can be reactive in that if the level of interference as reported by our dynamic ML interference modeling technique is significant for two co-located applications, one of the applications could be migrated to another virtual machine that is better suited. Or placement strategies can be proactive, in which two applications are evaluated for compatibility prior to being co-located. That is, a placement strategy could avoid co-location of the two microservices and seek an alternate placement if they are deemed incompatible. This concludes the presentation of our work.